So hello, I'm Tom, and I'm going to be talking about my cosmic radiation levels project, which is a project I did as a split-off from the Lucid project you've already heard about so far, and I ended up doing an EPQ based on the results of this project. Now, the idea behind this project basically came from the question of, well, basically, the main reason we can't send astronauts onto prolonged space missions such as to go to Mars is due to cosmic radiation. The radiation levels are so extreme that the astronauts would put themselves in danger being exposed for such a long time. And yet, astronauts are able to go onto the International Space Station for 6 months at a time and are allowed to go 3 times. And therefore, why are they able to go to the International Space Station but not able to go to Mars? And the reason for this is predominantly because the International Space Station, as you can see by this handy diagram, is still within the Earth's atmosphere. It's within the Earth's... My clicker has stopped working. Oh well. It's within the Earth's thermosphere, being 400 kilometers above the surface, which is still within a reasonably thick section of the atmosphere, and therefore still receives some protection from cosmic radiation compared to in outer space. Now, the school Lucid Satellite, on the other hand, is 700 kilometers above the Earth's surface, and is only within the Earth's exosphere, which is a very, very thin part of the atmosphere, and therefore receives much less protection from cosmic radiation. And so my project aimed to look exactly at the radiation levels both the International Space Station and Lucid receive, to see exactly how much more radiation Lucid detects and what effects that'll have. Now, the way I did this was using the TimePix chip, which you've heard about a lot today. And this chip, developed at CERN, consists of 256 by 256 pixels. And each of these pixels can detect whether they've been hit by a particle and with what energy they've been hit. And therefore, by taking the data from that, you can create these little, still not working, you can create these little 256 by 256 pixel images, where each one of the little tracks and dots on that image there is a particle that's been detected by the chip. And there's one of these chips aboard the International Space Station, as you've heard. Now, the Lucid Satellite, the Langton Ultimate Cosmic Ray Intensity Detector, has 5 of these TimePix chips attached to it in the shape of an open-top cube. And as I said earlier, it's outside the protection of the Earth's atmosphere. Now, by taking the data collected by these chips and putting it into the website TAPAS, you can get a reading for particle counts. You can find out exactly what particles they've detected and how many of them they've detected. Now, in order to actually compare the two, I took data from the TIMPIX chip aboard the International Space Station, which was a project where they activated their TimePix chip once every 10 minutes for one complete 90-minute orbit of the Earth. And for each one of these 9 data values, I've selected 3 Lucid data values from roughly the same latitude and longitude. And the idea behind this is that the radiation levels shouldn't be skewed by relative position in the Earth's magnetic field, or relative proximity to something like the South Atlantic anomaly, which is obviously higher radiation than anything else. And therefore, the only difference between the Lucid and the ISS datasets should, in theory, be their relative altitudes and protection from the atmosphere. Now, once you put the data into TAPAS, you get it in a format like that. And that's not actually particularly helpful. There's all sorts of particles on there. There's different frame numbers. The chips are left on for different times, and you can't really draw any significant information from it. So what I did to get something you could use was I focused entirely on the protons that were detected. Because as was mentioned in the first talk, protons make up about 85% of cosmic radiation. And out of the particles that we can detect, they're the ones that are most significant in terms of creating the dangerous effects of cosmic radiation. And also, I converted the various proton counts into the number of protons at each frame detected per second. And therefore, by both sets of data being transferred into protons per second, you can directly compare the two to see which one had more and by how much. And when I did this, the graph's gone a bit weird for some reason. But when I did this, I got the results that you can see here, which is actually, it's gone a bit off. But as you can see here, the results for Lucid in red are much, much higher than the results for the ISS, which are in yellow. In fact, you have to look pretty closely to see the ISS results. And the results table on the left is the same information. And you can see, say, for position 4, Lucid picked up 64 protons per second, whilst the ISS only picked up about 2. And averaging all this out, I found out that on average, Lucid detects about 220 times more radiation than the ISS does. And even if you remove the most anomalous data values, that value is still 90 times higher. And if you look specifically at, I think, position 6, 148 protons per second versus 0.1, that showed it as being 3,400 times higher in outer space compared to the ISS. And to put this value 220 times more extreme into real-world context, by looking at various papers that have been published, you can find out that the average radiation dose received by astronauts on the ISS is 72 millisieverts throughout their entire mission, or about half a millisievert per day. And 1 millisievert, for context, is roughly the amount of radiation that someone receives due to just background radiation in a year. Or if you were paying particular attention to the first talk on the Medibix collaboration, due to various things like medical procedures, that's actually closer to about 3 millisieverts per year. So, on the International Space Station, astronauts receive about in a day they receive about half to a sixth of the amount of radiation that we all experience in a year per day, which is quite a lot of radiation, but it's not really that damaging. It's not causing many problems. And indeed, a NASA astronaut is only allowed to go up 3 times before they've been deemed to have too much radiation, but they're not allowed to go up again. And using my value that radiation in outer space is 220 times more extreme, you come up with a value that the radiation dose in outer space would be 87 millisieverts a day, which if we use the limit that astronauts at NASA are allowed to receive in their entire career, which is 360 millisieverts, you can see that an astronaut in outer space would only be able to be in outer space for 4 days before they would receive so much radiation that they would be called back off the mission, which is not exactly helpful. There's not many research projects you could do in 4 days in outer space. And to put this into a trip to Mars context, at the moment, current trips to Mars are guessed to take about 200 days to get from here to Mars. And that would mean that you'd receive about 17,000 millisieverts in those 200 days. And using the NASA read limit, which is what NASA uses to calculate average chance of death due to radiation exposure, you can see that this would result in a 50% chance of death on the way to Mars, and then a 50% chance of death on the way back from Mars as well. And therefore, that's not exactly, they're not really going to be able to convince many people to fund a trip to Mars if about half the astronauts are going to die on the way there, and about half of them are going to die again on the way back. And also, for this sort of thing, is because cosmic radiation is it varies so much. You can either be hit by a sudden extreme amount of radiation or a sudden lax amount of radiation. It's worth preparing for a worst case scenario. It's worth preparing missions for if they were hit by, say, a solar flare or a sudden spike in radiation. So using my, the position 6, using the 3,400 times larger radiation estimate, you would see that the chance of death for a mission to Mars would be 800%. And I would like to stress that this is 800% on the way there, and 800% on the way back. And for context, that's not 7, that's 8 times the amount NASA it's 8 times the amount NASA believes will be guaranteed to kill someone. At that point, you're going to have difficulty bringing their bodies back. They've received so much radiation. And therefore, you can see from this that extended space missions have a serious problem with viability of cosmic radiation. I mean, going to Mars is really the next thing we can do from going to the moon. And at a 50% death rate for there and the way back, that's really not viable. So the main way that there are 2 things we can do to basically improve the odds and make a space mission viable. And one of those is to improve our radiation shielding. And therefore, if we have better radiation shielding, reduces the amount of radiation astronauts would receive, and receive less of a dose. But at the moment, I did put this into current radiation shielding, and I worked out that the chance of death falls to 45%. So well done. 5% off. But so obviously, in order to get to a viable mission, we're going to have to vastly improve our radiation shielding. And of course, with radiation shielding comes bigger, heavier spacecraft that are harder to move. What seems a more likely method of being able to get to Mars is simply to get there faster. Because as I said, the average dose is 87 millisieverts per day, which means the less time you're in space for, the less dose. In fact, if you were able to get to Mars within 4 days, you'd still be within the career dose limit. And interestingly, Elon Musk, who's currently forwarding the SpaceX program, his idea is to get to Mars in 30 days, which obviously would massively reduce the radiation from the current 200-day estimate. Although for a bit of fun, I did put that into my data and found out that that would result in a 7% chance of death, which is a vast improvement. But I do wonder if he's told the crew that 7% of them won't make it, and 7% again won't make it on the way back. So, to round this all up, the final conclusion that you can take from these findings is, don't go to Mars, you'll probably die on the way back.